All right, good afternoon. Today I would like to discuss the heart, the four chambers of the heart, the heart valves, which prevent backflow, the direction of blood flow through the heart, even the space that the heart sits within, and the major inlet and outlet vessels that are bringing blood to and from the heart. So our heart discussion is the key. So when you look at the book and the PowerPoint, what I'll do is I'll share the screen so you can see what I'm seeing, and I'll open up our chapter here of the cardiovascular system. When you look at pictures of the heart, you often see the outside of the heart, where we can point out some of the major blood vessels, like the vena cava bringing blood to the right side of the heart, like the pulmonary artery bringing blood to the lungs, or the aorta bringing blood to the body. But we can also see, when looking at the outside of the heart, some of the blood vessels that actually feed the heart itself, that we call the coronary vessels, because they surround the heart like a crown of vessels. So when you hear coronary, it means crown vessels, but it relates to the heart. They could also be called cardiac arteries and veins, but they're referred to as coronary. So we last left around page 672 or so, and we were talking about the heart. And this is a picture of the heart with blood flow going through it. I'm going to show you another version of that from the internet that's a little bit, the blue is filled in, so it's a little easier to see the parts. And then when you look at the outside of the heart, again, here's one outside picture, and what it's doing is it's showing you the casing around the heart that we call the epicardium. Then it slices it open, and you can see the muscle of the heart, which is actually a three-layered weave of muscle fibers. That way there's a squeeze effect. So it's not just contracting like a typical muscle, shortening end to end. It's actually got oblique fibers as well as a set of circumferential fibers, so that you get a circular squeeze plus perpendicular squeezing, almost like if you're icing a cake and you're pressing against the bag while squeezing it and twisting it to get the icing to come out. That's the way the heart muscle contracts to squeeze the chambers to make for less space that the blood is within. So that's the reason for the muscular wall. And then there's an inner lining that we call the endocardium. So epicardium, myocardium, and endocardium, and all that inside of what's called a pericardial sac. But I'm trying to show you an outside picture of the heart so you can see the blood vessels, and all it does is it talks about it without a picture. So we're going to use the advantage of pictures today, because illustrations and animations, and I even have video of heart dissection for you to look at, so you can really get a nice appreciation of this thing we call the heart. So let me go first to a heart picture. And if you're looking on the screen and you see what I'm seeing, you should see what looks like a blue and a red thing. The blue side of the heart is the right side of the heart, and the red side of the heart is the left side of the heart. All right. So it's not a bad idea on tests or when learning about this stuff, when you're looking at a picture of the heart like this, put an R over here for right, put an L over on this side for left, so that you remember that you're looking at somebody else's heart straight on. So everything is on the opposite side of what you know. This is the left side of the page looking at it. This is the right side of the page looking at it, but it's the heart's perspective, the other person's heart. So this is the right side of their heart. And the first chamber that we see is called the right atrium, which is this inlet chamber with arrows coming into it. Remember what we said yesterday, atrium as a word in Latin is the entry room. So like the foyer, or the room of entry. So this is where blood comes into the heart, into the right atrium. And the blood has come from all over all over the body. Think of the blood cells, if you will, as pilgrims, and they're on their Mecca, searching for the Mecca, so that they can enjoy living life inside of the body. And their place of, I guess we'll call it the place of worship, is the heart. Okay, so the blood cells come from all over the bones of the body. When they're made in the bone marrow. They enter into the capillaries of the bone, which open up to veins, and veins drain toward either the inferior vena cava for the lower body, the superior vena cava for the upper body, and then some vein of the outer heart itself coming back into this right atrium. So the blood cells have made this journey from the body, somewhere in the body, but eventually come into this right atrium. The right atrium is only so big as blood fills into the atrium. It fills to its relative capacity, and then it starts to contract. And the contraction pushes the blood directionally toward this right ventricle. Okay, it goes through a doorway that looks somewhat like a tent or a TP system. This first doorway actually has 3 leaflets, or 3 valve cusps. So it's referred to as the tricuspid valve because of its 3 cusps. As the blood comes into the right ventricle is relaxed and filling, while the right atrium is squeezing, and the blood is going from one chamber into the next. All right. Once the blood is here in this right ventricle, the right ventricle will start to contract. When that happens, the force of contraction pushes the 3 cusps of the tricuspid valve shut, so that there's no back pressure, allowing blood to go back into the right atrium. And all of the blood then gets forced in an upward direction toward what's called the pulmonary trunk, also referred to as the pulmonary artery. Well, it will become the right or left pulmonary artery. It's the trunk initially, and then it branches to its arteries. But there's a valve, a different type of valve, a flimsier valve, referred to as a semilunar valve because of its cusps looking half moon shaped, and it's curved into the vessel of the trunk, so that when pressure of the ventricle creates a squeeze, it opens up those valves, pushing blood into the pulmonary trunk, closing the valve. That's what we call the atrioventricular valve. This tricuspid valve is an atrioventricular valve because the valve between the atrium and the ventricle. That valve is shut, pushing the blood forward into the pulmonary trunk, and pressure then takes the blood on a journey away from the heart. So now it's not really a heart thing anymore, because blood is now leaving the heart. But it's only going to one place. Well, I guess I could say it's going to 2 places. One on the left or one on the right, depending on if pressure takes it to the left or the right. Either way, the ultimate destination of this is the same, because whether it's the right or the left, there's going to be a lung. And the arteries are going to be getting smaller and smaller as they branch throughout the lungs, until they're tiny, tiny blood vessels that surround balloon sacs of the lungs called alveoli. This is where oxygen from the air is exchanging with the blood, and the hemoglobin on the red blood cells is sponging that oxygen out of the air. Let me do something here. There we go. So the hemoglobin that is in the red blood cells, as it goes to the right side of the heart, is not oxygen rich. It makes the blood darker red. And then as it leaves the heart from the right ventricle into the pulmonary arteries, the blood is still oxygen poor, but under pressure from the squeezing ventricle, that blood quickly moves into the lungs, through the vessels of the lungs, into the smaller arteries, into the arterioles, eventually the capillary bed that surrounds the alveoli. The alveoli are air-filled, and this is where diffusion of oxygen can occur. It diffuses through the membranes of the capillaries, through the membranes of the alveoli, and then the hemoglobin sponges that oxygen to it. Well, the capillaries don't come to an end. They just continue, and they open up to larger venules, which become veins. And eventually, two large veins from the right lung and two large veins from the left lung bring oxygen-rich blood back directionally to the heart, where they will enter blood into the left atrium, which is somewhat of a mirror image of the right atrium, except for the blood coming into it is coming from the lungs. And then that atrium will squeeze and push blood through the open bicuspid valve, also called the mitral valve because of its resemblance to a bishop's mitre. I don't know if you're familiar with what a bishop's mitre, but I want you to think of the Pope or a bishop having that hat that comes up above their head, coming to a little bit of a V. You see how my hands are, right? A mitre kind of looks like that. So the valve actually looks like that. If we look at the valve in 3 dimensions, it looks like it's a tent a little bit, but of 2 cusps. And that tent comes into the left ventricle. So when it's open, blood goes into the ventricle, but when it's forced shut, it shuts so where blood can't go back into the atrium. Remembering that atrium means entry room, ventricle means little belly. So the atrium is the receiving chamber for blood, and that's smaller than the size of, at least the size of the volume of what you can see going into the ventricle, which means the ventricle will only be pumping the volume of the atrium rather than the volume of the ventricle. The ventricle is roughly twice the size of the atrium as far as overall area and space. So it's working half as hard when it goes and it pumps, shutting the mitral valve, opening the opening the aortic valve, the valve between the aorta and the left ventricle, and then the blood ejects under a lot of power into the aorta, where pressure is going to take it wherever pressure is going to take it. Now, what you can't see, because this is inside the heart, is that immediately in the aorta, there's a small opening on the right and the left, which goes to the vessels that actually come back around to the outside of the heart and become the coronary arteries. So you actually have the left and right coronary artery coming off the very, very base of the aorta. But when blood doesn't go into the coronary vessels, it continues up the arch until it goes to the right limb, head, and neck, or it goes to the left head and neck, or goes to the left limb, or maybe stays and goes down the arch and behind the heart, where it's going to then feed the abdomen and go to the legs. That left ventricle has to be super strong because it is squeezing blood to the whole of the body, whereas the right ventricle is only squeezing blood to the lungs next door. So when you talk about the 4 chambers, there are 2 atria that are somewhat mirror images of each other, and 2 ventricles, which, for the better purpose of arguing, even though the ventricle on the left is considerably bigger, much more circular in shape, whereas the ventricle on the right is more crescent shaped, you can still, from the point of view of trying to learn these chambers, call them somewhat mirrors. So what you're having is a right side, which is going to send the blood to the lungs, and a left side, which is going to send the blood to the body. And to give you an idea of how this works, while the right side is pumping, the left side is not resting. The left side is pumping also. So the right side and the left side atrium look like they're both squeezing at the same time, while both ventricles look like they're filling at the same time. Then both ventricles look like they're squeezing at the same time, while the 2 atria are filling to start the cycle new. So it looks like this: atria ventricles, atria ventricles, atria ventricles, atria ventricles, atria ventricles, atria ventricles. But if we were to slow that down, instead of it looking like atria ventricles, it would actually look like this: right atrium, left atrium, right ventricle, left ventricle, right atrium, left atrium, right ventricle, left ventricle, right atrium, left atrium, right ventricle, left ventricle. So there's a little bit of a tiny split between the right side and the left side. And that's so quick, the right side working with the left side, that when we look at the heart, it looks like they're both squeezing simultaneously, and it looks like, and even sounds like it under a stethoscope. If we were to truly record the heart beating and then slow it down slow it down visually, slow it down audibly, we'd start to see and hear the split between the right and left sides. But to the naked ear under with a stethoscope or just watching a heartbeat, it looks like the two atria are contracting together. It looks like the two ventricles are contracting together. So that blood flow is moving through both sides of the heart at the same time. And the reason why the right side actually starts before the left side has to do with the conduction system, which is an electrical system of, if you will, wires that are built into the heart muscle so that there's a rhythm and a coordination to how the heart contracts. All right, let's look at some other views here of the heart. All right, so this is what I meant by the outside of the heart, where you can see the coronary vessels. These are the coronary vessels. Okay, this is the right coronary artery coming out in the red, and then with its branches feeding the heart. This is the left coronary artery coming around and feeding the heart. This is what we just looked at. This is another view of looking at the inside. Always notice the direction of arrows. If the direction of arrow is going into the heart, it's venous. Okay, I don't care if it's red or blue. These red arrows are coming into the heart. Those are veins. These blue arrows are coming into the heart. Those are veins. But coming out of the heart, if it's going away from the heart, it's an artery. Here's a blue artery. Here's a red artery. But what it is outflow. Arteries, arterial blood, they have drawn here as red, but that's wrong. Okay? It should be saying oxygen poor blood, oxygen rich blood. What makes it red is oxygen poor or oxygen rich. What makes it blue is oxygen poor. But the direction of arrows has everything to do with whether it's an artery or a vein. Arteries are always taking blood away from the heart. I don't care if it's going to the lungs. I don't care if it's going to the body. It's an artery taking blood away from the heart. They are built strong enough, elastic enough, thick enough to endure the pressure of the squeezing heart. Veins are flimsy. They are not designed for pressure. They are always bringing blood back directly to the heart. So here's a more involved look at the heart. We see blood coming into the heart from the lower body, from the inferior vena cava, which means the lower cavernous vein, which means just big open space vein. We see blood from the upper body coming through the superior vena cava. And if I go back a picture, these blood vessels right here, these blue ones, they're taking blood back into that right atrium as well. So it all comes into the right atrium, and then through that open tricuspid valve, blood ejects into the right ventricle. Right ventricular blood, they get squeezed. The tricuspid valve is pushed shut, opening up the pulmonic valve or pulmonary valve, which is the valve that prevents blood from the pulmonary trunk coming back into the right ventricle. And then blood goes under a lot of power and force toward the lungs. Now, I want you to notice this little structure right here, if you're looking at the screen and the picture, between this blue arrow and this red arrow, we see the aorta, we see the pulmonary trunk. There's this little, what looks like a stitching. That is referred to as the ligamentum arteriosum, which means the artery ligament. All right. Why is there an artery ligament? Because a ligament is designed to hold bone to bone, right? Well, it's called a ligament because it looks like it's holding the two vessels together. But in reality, what it really is the remnant of a one-time vessel that connected the pulmonary trunk to the aorta that allowed blood to go from the pulmonary trunk directly into the aorta. That only happened while you were in the womb. While you were in the womb. And this allowed blood to not have to go to the lungs because guess what? You're not breathing air in yet. So you don't need all this blood going to your lungs yet. They're not developed. They're not mature yet. So blood is bypassing some of the lungs by going directly from the pulmonary trunk into the aorta and then to the rest of the body. Another little area that we see, I don't know if you can see it, there's a little dark area right here in the right atrium. It's called, in the developed heart after you're born, it's called the fossa ovale, which means the oval depression. That was not always a depression. At one point in time when you were developing in the womb, that was an opening that actually connected the right atrium to the left atrium, so that blood coming into the right atrium could actually go directly over to the left atrium and then get sent to the left ventricle and on. So there was another bypass called the foramen ovale, the oval hole, and that closes. Okay, at least it's supposed to close, and when it closes off, it becomes a depression. So all these are examples of what we call intrauterine life of the heart, or if you will, what goes on while inside the womb while the heart is developing. If you never remember that there's a one-time artery when you're in the womb, or a one-time opening between atria when you're in the womb, you'll still be fine. But later on, there's going to be a video I show you where the presenter, Dr. Ackland from Louisville Med School, he mentions the fossa ovale, and he says the one-time remnant of the foramen ovale, but he doesn't really go into explaining what that is. So I'm just letting you know in advance. Now, with that said, blood going from the right atrium goes through the tricuspid valve into the right ventricle, gets pumped through the pulmonary semilunar valve into the pulmonary trunk, where it either goes to the right pulmonary artery to the right lung or the left pulmonary artery to the left lung. And again, inside the lung, the blood vessels get smaller and smaller and smaller until the blood is in capillary, squeezing through single file and being exposed to the lungs' balloon sacs, where air with oxygen in it fills the balloon sac, and then the hemoglobin from the red blood cells able to sponge up the oxygen from the lungs. But then the blood has to make a journey back from the lungs to the heart. The right lung has eventually these two large veins that come into the left atrium. The left lung has these two large veins that come into the left atrium. So those four veins bring blood from both lungs back to this left atrium. The left atrium then pumps the blood into the left ventricle through this bicuspid or mitral valve. And then the left ventricle, which is super thick, if you can see it on this picture, super thick, squeezes, the blood does a 180-degree turn and is shot into the aorta, where it then feeds the rest of the body oxygen-rich blood. So the goal is to understand the four chambers of the heart, knowing the two inlet chambers of atria and the two pumping chambers of ventricle. But unless you also know the atrioventricular valves, like tricuspid and bicuspid, that prevent backflow of ventricular blood into the atria, or if you don't know the semilunar valves, pulmonic and aortic respectively, that prevent backflow of blood from the vessels into the ventricles, then it doesn't complete the discussion. You have to have this understanding that there needs to be valves in place, these doorways in place, to prevent blood from going the wrong way. The heart is about creating the squeeze, the push, the pressure into the arteries. And if the valves don't work, blood going the wrong direction decreases the amount of ejection force, decreasing the amount of push or pressure that the heart can create for the bloodstream. So what I'd like to do now is show you Dr. Ackland's video so you can see the dissected heart. And then I'm going to show you animation of blood flow going through the heart. In other words, we're going to see the heart. We're going to see inside of the right atrium, inside of the right ventricle. We're going to see the pulmonary trunk. We're going to look inside the left atrium. We're going to look inside the left ventricle. We're going to see the mitral valve. We'll see the tricuspid valve. We'll see the aortic valve and the pulmonic valve. All right, as Dr. Ackland explains the heart. So let me put him on. I will say one thing about Dr. Ackland. It's a very well presented dissection, but he is maybe on the monotone side slightly. Um, he's definitely trying to point out a lot of the structures. So you'll see what I mean. He says this is here, this is here, and this is here. This is here, and this is here. This is here, and this is here. So if you follow along with it and really just admire the word in my head is cleanliness, but it's not cleanliness. It's how meticulous the dissection is and the demonstration. I think you can appreciate the heart and its anatomy. Here we go.
This tape shows the internal organs of the thorax and of the abdomen, and the male and female reproductive organs. In this first section, we'll look at the organs of the thorax, first the heart, then the lungs. We'll also look briefly at the esophagus. The thorax itself, upper part of the trunk which contains the heart and lungs, is shown in tape 3 of this atlas. Here, we're looking at the contents. To understand the heart, we'll begin by seeing where it is. We tend to put the heart here in our imagination, but in reality, it's much closer to the midline. Seen from in front, the heart is here. It lies behind the sternum and directly above the diaphragm. Seen from the side, the heart is here, occupying almost all the space between the vertebral bodies behind and the sternum in front. When the diaphragm moves, the heart moves with it. To get our first look at the heart, we'll start by removing the upper extremities and all the shoulder muscles that surround the upper thorax, so as to leave just the thorax itself, enclosed by the ribs and intercostal muscles. Then we'll remove this part of the rib cage on each side, revealing the lungs, which are fully inflated here. When we let the lungs deflate, we can see the heart behind the sternum, contained within its protective jacket of pericardium. To see it better, we'll take the lungs, the sternum, and the pericardium out of the picture. This is the heart. This is the diaphragm. The major blood vessels that lead into and out of the heart take up almost as much space as the heart itself. Now that we've seen where the heart is, we'll take a detailed look at it. We'll look at its 4 chambers and its 4 valves. Then we'll look at the great vessels that enter and leave the heart. And lastly, we'll look at the coronary arteries. Because we so often see simplified diagrams of the heart like this, we tend to think the atria, the inlet chambers, are above, and the ventricles, the pumping chambers, are below. It's perhaps surprising to see that in reality, the atria aren't above the ventricles, they're behind them. Here's the heart in isolation. Here are the ventricles in front. Here are the atria behind. This generous coating of epicardial fat makes it hard to see the 4 chambers distinctly. To see them more clearly, we'll go to a heart in which almost all the fat has been removed. In this specimen, all 4 chambers have been distended with equal pressure, making the atria somewhat larger than normal. This is a directly posterior view of the heart. This is a directly anterior view. The massive thick-walled left ventricle projects forward and to the left. The thinner-walled right ventricle is partially wrapped around the left one. We'll see the ventricles by themselves in a minute. For now, let's go around to the back and look at the two atria. This is the left atrium. This is the right atrium. Blood coming from the upper part of the body enters the right atrium by way of the superior vena cava. Blood coming from the lower part of the body enters it by way of the much larger inferior vena cava. In a more intact dissection, here's the inferior vena cava coming up through the diaphragm and almost immediately entering the right atrium. In addition to the two venae cavae, blood from the heart itself enters the right atrium under here by way of the coronary sinus, which we'll see later. From the upper part of the right atrium, this blind pouch, the right auricle or atrial appendage, projects forwards. The thin wall of the right atrium is formed largely of muscle. When the atrium contracts in diastole, blood in it passes forwards into the right ventricle through the right atrioventricular valve or tricuspid valve, which is here. The left atrium and the right atrium are in contact here, where they share a common wall, the interatrial septum, which lies quite obliquely. To look at the inside of the right atrium, we'll remove this part of its wall. Here's the opening of the superior vena cava above and of the inferior vena cava below. Here's the opening of the coronary sinus. This is the part of the atrial wall that's shared with the left atrium, the interatrial septum. This thin oval patch in the septum is the fossa ovale, the remnant of the foramen ovale that connected the two atria in intrauterine life. Here we're looking forwards into the tricuspid valve. We'll see more of it when we look at the right ventricle. Now we'll move on to look at the left atrium. Blood coming from the lungs enters the left atrium by way of the four pulmonary veins, two from the right lung, two from the left. The left atrium, like the right one, has a blind pouch, the left auricle or atrial appendage, which projects upwards and forwards. In diastole, the blood that's in the left atrium passes forwards into the left ventricle through the left atrioventricular valve or mitral valve, which is here. To see inside the left atrium, we'll remove this part of its wall. With the four pulmonary veins removed, the inside of the left atrium is relatively featureless. Here's the interatrial septum again, and here's the remnant of the foramen ovale, seen from the left side. Here we're looking forwards into the mitral valve. Now we'll move on to look at the two ventricles and their inlet valves. To see them clearly, we'll look at a heart in which the right and left atrium have been removed, leaving just the two ventricles. Here's the right ventricle, seen from the right side. Here's the left ventricle, seen from the front. Going round to the back, this is the right ventricle. This is the left one. They're separated by the interventricular septum, which is here. We're looking forwards into the wide open atrioventricular valves, the tricuspid on the right, the mitral on the left. On the right side, blood passes downwards and forwards to fill the right ventricle in diastole. Then, in systole, it passes upwards and to the left into the pulmonary trunk, passing through the pulmonary valve, which is here. On the left, blood also passes downwards and forwards to fill the ventricle, then gets turned completely around in systole, passing upwards and backwards into the aorta. It passes through the aortic valve, which is out of sight, here. To see inside the right ventricle, we'll remove this part of its wall. tricuspid valve is here. We'll look at it in a minute. Pulmonary valve is up here. The anterior part of the right ventricle, the apex, extends out of sight down here among these intersecting bands of muscle called trabeculae. This is part of the interventricular septum. The left ventricle is on the other side of it. Now let's take a look at the tricuspid valve and its appendages. The tricuspid valve is also called the right atrioventricular valve. It usually has 3 cusps, sometimes only 2. Here there are 3. They're known as the septal, anterior, and posterior cusps. The posterior cusp is partly out of sight. These strands of tendon-like material attached near the edges of the valve cusps are the chordae tendineae. They arise from papillary muscles, which project from the wall of the ventricle. The papillary muscles and chordae tendineae prevent the cusp of the valve from prolapsing back into the atrium during systole. Here's the tricuspid valve set in motion passively by an intermittent current of water. When pressure in the ventricle rises, the cusps of the valve close together along quite an irregular line. The inside of the right ventricle is made irregular not only by the tricuspid valve and its appendages, but also by these numerous bands of muscle, the trabeculae carni. The trabeculae form a dense crisscross pattern over much of the ventricular wall, especially here toward the apex. To see the outflow pathway of the right ventricle, we'll go to a different specimen. The tapering part of the right ventricle that leads up to the pulmonary valve is known as the infundibulum and also as the conus. Unlike the rest of the right ventricle, its lining is smooth. We'll look at the pulmonary valve in a minute. Now, we'll move on to take a look inside the left ventricle. We'll remove this part of its wall. The mitral valve is here. The aortic valve is out of sight up here. This is the apex of the ventricle. This part of the ventricular wall forms the interventricular septum. Here's the left ventricle in cross-section. Here's the right ventricle. The interventricular septum is curved. The left ventricle has a much thicker wall than the right, and it's circular in cross-section, while the right ventricle is C-shaped. Here, we're looking backward into the mitral valve. To see it better, we'll return to the previous dissection and go round to a view from behind. Mitral valve, also called the left atrioventricular valve, has 2 cusps. They're called the anterior cusp and the posterior cusp, though in reality they're more upper and lower. Chordae tendineae from both cusps converge on 2 sets of papillary muscles. These on the posterolateral wall of the ventricle, and these on the anteromedial wall. Here are the same papillary muscles seen from the apex of the ventricle. Each group of papillary muscles sends chordae tendineae to each of the cusps of the mitral valve. Here's the mitral valve in motion, seen from the apex of the left ventricle. Here are the papillary muscles, seen very close. Above the mitral valve, we're looking upward and backward along the outflow tract of the left ventricle, toward the aortic valve. In this cutaway dissection, we can see the outflow tract of the left ventricle from the side. Here's the aortic valve. We've left intact part of the anterior cusp of the mitral valve, along with the chordae tendineae and papillary muscles. The anterior cusp of the mitral valve forms part of the wall of the outflow tract, so blood flows past it this way in diastole, and this way in systole. Here's the anterior cusp of the mitral valve in motion, with mitral valve opening below it, and the outflow tract above it. Now that we've seen both ventricles, we'll move on to look at the two outflow valves, the pulmonary valve and the aortic valve, and also at the pulmonary trunk and the first part of the aorta. Here are the two ventricles, dissected so that we can see the outflow valves. Here's the aortic valve. Here's the pulmonary valve. Each has three cusps. The pulmonary trunk and the aorta are markedly dilated at their origins. On each vessel, the dilatation consists of three bulges, or sinuses, whose position matches the position of the valve cusps. To get a better look at the cusp of the outflow valves, we'll remove these parts of the vessel walls. Each cusp of an outflow valve is shaped like 1/3 of a parachute. Here the cusps are hanging loose. Each cusp has a delicate free border which closes against those of its neighbors. Here's the pulmonary valve in motion. In diastole, back pressure closes the valve abruptly, the three cusps pressing against each other to meet exactly at a point. Here's the aortic valve. It works in just the same way. Here's the opening of the right coronary artery, which we'll see in a minute. The left one is out of sight down here. Now that we've seen the outflow valves, we'll move on to look at the two major outflow vessels, the aorta and the pulmonary trunk. To see them, we'll go to a more intact dissection. The pulmonary trunk passes backwards to the left of the aorta, then divides into the left pulmonary artery and the right pulmonary artery. The right pulmonary artery curves around above the left atrium, passing behind the root of the aorta and behind the superior vena cava. This early branch supplies the superior lobe of the right lung. This cord is the divided ligamentum arteriosum, the remnant of the ductus arteriosus, which connects the pulmonary trunk and the aorta in intrauterine life. Here's the aorta. It starts to the right of the pulmonary trunk. Its beginning is well hidden in the epicardial fat. In front of it is the right atrial appendage. To its right is the superior vena cava, and behind it is the right pulmonary artery. Next, we'll take a look at the coronary arteries, which provide the vitally important blood supply to the heart itself. The detailed branching pattern of these vessels is highly variable. What we'll see here is just one example. To see the coronary arteries, we'll look from above at a heart from which most of the epicardial fat has been removed. Here's the pulmonary trunk. Here's the aorta. To see where the coronary arteries arise, we've removed both atrial appendages. The left atrial appendage was here. The right atrial appendage was here. Here's the right coronary artery. It arises from the right aortic sinus, which is here. The right coronary artery gives up this branch to the upper part of the right atrium, then runs downwards in the right atrioventricular groove, giving off branches to the right ventricle. The right coronary artery passes round to the underside of the heart. Here it is again. Its terminal branch is the right interventricular artery. Now, we'll look at the left coronary artery. Here it is. It arises behind the pulmonary trunk from the left aortic sinus. The left coronary artery soon divides, giving off this circumflex branch and several branches to the left ventricle, the longest of which is the left interventricular artery, also called the left anterior descending artery. The circumflex branch of the left coronary artery runs around to the underside of the heart in the left atrioventricular groove, sending further branches to the left ventricle. The blood that goes out by way of the coronary arteries returns mainly by way of a system of coronary veins, which join to form a large venous channel, the coronary sinus. As we saw earlier, the coronary sinus ends by entering the underside of the right atrium, here. Here's the coronary sinus in an intact heart. The coronary sinus passes around the left interventricular groove to the underside of the heart. Its opening into the right atrium is just below and in front of the inferior vena cava. Coronary veins from the right side of the heart also empty into the coronary sinus. Now that we've seen some dissected specimens, let's take a further all-around look at an intact heart with all the epicardial fat intact. We'll take a second look at all 4 chambers in the order in which blood passes through them. Here's the right atrium with the superior vena cava entering above and the inferior vena cava below. Here's the right atrial appendage. Here's the location of the tricuspid valve. Here's the right ventricle. It's almost obscured by fat. Here's the infundibular. The pulmonary valve is here. Here's the pulmonary trunk passing to the left of the aorta and dividing into the left pulmonary artery and the right pulmonary artery. Here's the left atrium with 2 pulmonary veins entering on the right and 2 on the left. Here's the left atrial appendage. The mitral valve is here. Here's the left ventricle. Its outflow pathway is here, leading to the aorta. Here's the aorta, and the aortic valve is here. So far, we've been looking at the heart by itself, with the major vessels that leave and enter it divided. To see where those vessels go, and also to see the pericardial sac around the heart, we'll look at a dissection in which the anterior chest wall has been removed from the first rib to the 8th rib. The diaphragm is here. On each side, the lungs are quite collapsed. If they were fully expanded, they'd be out to here. Here's the heart, hidden within its protective sac of pericardium. In the intact body, the front of the pericardial sac is attached to the back of the sternum by this strip of mediastinal fat, all of which we'll remove. All this is the pericardial sac. The only major vessels we can see at this point are the aorta, emerging from the pericardial sac here, and the superior vena cava, entering it here. To see more, we remove this much of the pericardium. Here's the heart, well covered with epicardial fat. The ventricles are freely mobile within the pericardial sac. Below, the pericardium is reflected onto the upper surface of the diaphragm, to which it's densely adherent. To right and left, pericardium lies back to back with the parietal pleura. Here's the root of the aorta and of the pulmonary trunk. Here's the superior vena cava, entering the right atrium from above. Each of the great vessels passes through an adherent cup of pericardium as it enters or leaves the pericardial sac. Here's the inferior vena cava, coming up through the diaphragm. Here are the left pulmonary veins and the left pulmonary artery passing through the pericardium separately. On the right, the pulmonary vessels are harder to see because they lead through a continuous cuff of pericardium that they share with the inferior vena cava. Here are the pulmonary veins. The artery is out of sight up here. Once we've understood the heart in 3 dimensions, understanding the great vessels that enter and leave becomes straightforward. Superior and inferior vena cava and the aorta are shown in tape 3 of this atlas, and we'll see more of the pulmonary artery and veins later in this section. Now let's review what we've seen of the heart. Here's the right atrium, the atrial appendage, superior vena cava, and the inferior vena cava. Here's the interatrial septum, the fossa ovale, the opening for the coronary sinus, and the tricuspid valve. Here's the right ventricle. Here are the papillary muscles, and the chordae tendineae, and the infraventricular. Here's the pulmonary valve, and the pulmonary trunk, branching into the left pulmonary and the right pulmonary. Here's the left atrium. Here are the pulmonary veins, right and left. Here's the interatrial septum again, and the mitral valve. Here's the left ventricle, the interventricular septum, the left ventricular outflow pathway, the aortic valve, and the aorta. Here's the left coronary artery. Here's the right one. Here's the coronary sinus. Here are pericardium and pericardial sac. Now, we'll move on to look at the lungs.
And since start discussion, we are not going to look at the lungs. But I do want you to see blood flow going through the heart. And that sometimes helps when you have animation rather than just photographs or illustrations of it. So let's look at some blood flow through the heart. All right. So that's Leslie Samuel's version. I'm pretty sure something similar, but we're just going to do some things that allow you to see it. All right. That one's okay. That one's all right. Heart failure there. 3D animated circulatory system and its functions. So let's start with this one.
You are the future. Pursue tech careers with the DeVry Scholars Program. Advance your ambition.
Okay, let me show you why I recently canceled my expensive dorm.
Not that one. There are this one's okay. So I will show you this one eventually, but I want to talk about a few other things first before I show you that. So we're gonna start with this one. Okay, a couple of things that I did not mention before that you heard with Dr. Ackland's video. He said the words systole and diastole, and those are just words of whether or not the heart is squeezing or filling, if it's contracting or relaxing. In other words, the chambers when they're filling with blood, those chambers are they're in a form of diastole. When they're squeezing the blood out, that's called systole. So systolic is the pressure created by the squeeze or contraction of the ventricles, and diastolic is the filling of the ventricles. Now, it is true that you could say atrial systole or atrial diastole also, but because the pumping chambers are where blood is leaving the heart, that's where we're describing systole or diastole by themselves. So diastolic is the filling of a chamber, systolic is the contracting of a chamber. So now let's watch. no narration. There's no narration on that, just music. Could you hear the music on that? Huh. Then I need to share the video. Was Dr. Ackland's? Ooh, that's not good. That's not good. Hold on a second. Okay, well, let's try it. Let's see what happens with this. Tell me if you hear the music. Did you hear it that time? Okay. Woo. Okay. So this one just has music. What I'm going to do is I'm going to mute it. I don't know if I can mute. Yeah, I can. I can mute it. And then I'm going to play it, and then I'm going to describe what you're seeing. All right. So this is the outside of the heart. Those are blood vessels that feed the outside of the heart. Those are called coronary vessels. All right. And then these are the inlet and outlet chamber or flow of the heart. So whether there's pulmonary trunk or whatnot. Now you see the heart from the outside beating. Okay, again, these are the coronary vessels that feed the heart itself. Blood is being pumped into the aorta from the left side, into the pulmonary trunk to the lungs on the right side. When it opens up, these are the valves on the inside. This is the tricuspid valve, 1, 2, 3 leaflets. This is the bicuspid or mitral valve, 2 leaflets. This is the right ventricle. This is the left ventricle. Those are the papillary muscles with their tendon cords, chordae tendineae, to the valves. Valves open, valves closed, valves open, valves closed. Okay. That's from inside. This is from the, so if we were inside the atria looking toward the ventricles, that's what the valves would look like as they're opening and closing. Okay. Same valves. All right. The bicuspid valve here on the left, the tricuspid valve here on the right, because we're looking now down and into the heart from the atria. You can see the tendon cords inside the ventricles there. So the bicuspid, okay, so there's your bicuspid closing and opening. Those are the well, now we see the wire. That's the conduction system. The little wires that make the heart muscle contract rhythmically. Here are the atrioventricular valves versus the semilunar valves. And then again, the outside of the heart contracting, 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 pumping blood, pumping blood, pumping blood. All right. So that's the heart. Now let's find you some that actually have narration. And I'll unmute it. All right. No, this one I don't.
You can feel your heart thudding away every time you put your hand to your chest. But do you have any idea what's really going on in there, or what keeps your heart ticking as it should? Every day, your heart beats about 100,000 times, sending 2,000 gallons of blood surging through your body. Although it's no bigger than your fist, your heart has the mighty job of keeping the blood flowing through 60,000 miles of blood vessels that feed your organs and tissues. Food, water and oxygen are essential for the existence of human life. Blood transports all these substances through various channels called blood vessels. Blood vessels involves arteries, veins, capillaries. To keep the blood flowing throughout our body, we have a pumping system, and the heart is the pump, which is composed of muscle that pumps blood throughout the body, beating approximately 72 times per minute of our lives. The human heart has 4 chambers: the right atrium, the left atrium, the right ventricle, and the left ventricle. There are 4 valves in the heart. These valves are tricuspid valve, mitral valve, aortic valve, pulmonic valve. These valves are one-way valves. Now, you have seen the structure of the heart. Let us find out how it works. The blood becomes oxygen-rich by absorbing oxygen in the lungs. The function of the heart starts when oxygenated blood is carried from the lungs to the left atrium of the heart by means of the pulmonary veins. The left atrium relaxes, this blood is pumped into the heart. When the left atrium contracts, the left ventricle relaxes simultaneously. The left atrium pushes the blood into the left ventricle through the one-way valve. When the left ventricle contracts, the blood is pumped into the aorta, which carries oxygenated blood to the different parts of the body, except the lungs. Oxygenated blood reaches the different parts of the body through the blood vessels called the arteries. The arteries gets branched into capillaries, which then reaches to the different organs of the body. The blood then becomes deoxygenated, and the blood capillaries gets mixed and form thicker blood vessels called the veins. The veins carry deoxygenated blood to the heart. The blood vessels that carry deoxygenated blood to heart are known as the vena cava. The deoxygenated blood from different parts of body enters the upper right chamber of the heart, which is called the right atrium. The right atrium gets contracted, allowing the blood to flow into the right ventricle, which contracts with the expansion of the right atrium through the one-way valve. The right ventricle then contracts, pushing the blood into the pulmonary artery. The pulmonary artery carries the deoxygenated blood to the lungs for oxygenation. The lungs oxygenate the blood by exchanging of gases and flows back into the heart through the pulmonary vein, and starts the circulatory cycle all over again.
Yeah, I don't typically like when computers talk. One's okay. There's a couple that are really good. Couple that are really good on heart blood flow. This one from Nucleus Medical is really good, but there's a bunch of, it's almost like there's like 5 or 6 different brief shorts, and I want to make sure I discuss other things, show you other versions before you see that one. That's a heart attack. That's the National Geographic version. Watch, it shows actual blood cells going through blood vessels and through the heart. So there's a short, how the heart works. Give this one a try.
Imagine that you've hopped onto a red blood cell to tour the heart. You and your blood raft flow into the right atrium from the superior or inferior vena cava, the largest veins in your body. After reaching the right atrium, you have less than half a second to admire the scenery before the atrium contraction sends you down to the right ventricle. To get from the right atrium to the right ventricle, you will have slipped through your tricuspid valve. Heart valves function as perfectly timed doors and only allow blood to move in one direction. After you slide through the first set of valve flaps, they slam shut behind you and the ventricle contract. This sends you shooting upward through the pulmonary valve in the pulmonary artery. The pulmonary artery sends the blood toward the lungs, splitting it into many smaller tubes. You are eventually squeezed through the tiniest tubes into the lungs' alveoli. In these narrow tubes in the lungs, the red blood cells load up with oxygen, and carbon dioxide leaves the blood vessels. Then you and your oxygenated buddies flow back to the heart through the pulmonary veins. One of the pulmonary veins dumps into the left atrium. Soon after you reach the left atrium, a familiar process begins again as the atrium contraction sends you down through the mitral valve and into the final chamber, the left ventricle. From here, you will embark on an adventure through the body because the next ventricular contraction will send you bursting upward into the aorta. The aorta is a large tube that branches into many other smaller tubes to distribute newly oxygenated blood throughout the body. If you decide to continue with the tour, you may flow down to a toe before circling your way back to the heart in roughly 30 seconds. Now that you know how your heart works, it's time to take you on a fascinating tour of the digestive system to show you what happens to the food you eat.
Now I can show you this one. All right, so now I'm going to show you this one right here, and I'm going to show you the in parts, okay? So that we can discuss after each video.
Your heart is an extraordinary machine. During your lifetime, your heart's muscular walls pump blood into blood vessels branching throughout your body. Your heart has 4 chambers. 2 upper chambers, called the left and right atria, and 2 lower chambers, called the left and right ventricles, contract in a steady rhythm known as your heartbeat.
Okay. So if you look on the screen, you'll see the little diagram of the heart. It has it split 4 different ways. Right atrium, right ventricle, left atrium, left ventricle, and it's got them as the 4 chambers. The ventricles are pretty much contracting together. The atria are pretty much contracting together. All right. But right-sided blood stays right-sided to go to the lungs. Left-sided blood stays left-sided to go to the body.
Known as your heartbeat. During a normal heartbeat, blood from your tissues and lungs flows into your atria, then into your ventricles. Walls inside your heart, called the interatrial and interventricular septa, help keep the blood on left and right sides from mixing. Two valves sit like doors between your atria and ventricles to prevent blood from flowing backward into your atria. The tricuspid valve opens into your right ventricle, and the bicuspid valve, also known as the mitral valve, opens into your left ventricle. Strong, thin tissues, called chordae tendineae, hold your valves in place during the forceful contractions of your ventricles. Blood leaving the ventricles passes through another set of valves, the pulmonary valve between your right ventricle and pulmonary trunk, and the aortic valve connecting your left ventricle and aorta.
Of the 4 valves, the 2 that are semilunar, which you see here and here, on the inside, they look like parachute pieces. They're somewhat half moon shaped. They're very flimsy, and then they close. And they're almost identical to each other as far as the way that they look. One's inside the aorta, one's inside the pulmonary trunk, and they're going to prevent blood from going back in the ventricles. They are flimsy. When you look at the 2 atrioventricular valves, here is the bicuspid valve. There's the bicuspid valve. There's the tricuspid valve, right? There's both of them together. Bicuspid and tricuspid, right? Tricuspid here on the right, bicuspid on the left. They're between the atria and the ventricles, so they're called atrioventricular valves. They are heavier, they're bigger, they make a louder sound, and they have the tendon cords there because the forceful contraction of the ventricles in systole can actually cause those flaps to pop into the atria, and that's called a valve prolapse. And we don't want that to happen. So those tendon cords are there to prevent prolapse. But it's the reason why when you put a stethoscope up to the chest wall and you hear the heart sounds, you hear okay. So the heart sounds are the closing of the atrioventricular valves, which are a bit heavier, and then the free slapping of the semilunar valves. It's described in the old texts as lub-dub sound. Lub-dub, 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 lub-dub. But more recently, it's being taught as lub-dub, 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 lub-dub. So that you hear lub-dub, like the solid and then the slap, the solid and the slap, the solid and the slap. Because the sounds of the two valves shutting, two sets anyway, shutting, again, the atrioventricular valves close so close together that to your ear it sounds like one sound, even though it's actually right, left, right, left, right, left, right? If we slowed it down, we'd actually hear the split. And then the same thing with the aortic valve and the pulmonary valve. The pulmonary valve and the aortic valve, they close so close together, it sounds like one slap, even though you could technically hear them as a slap. In fact, if somebody has had a heart attack and there's scar tissue and it slows down the conduction system around the heart, you might hear, instead of lubbed up, you might hear la-lub-da-dup, 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 la-lub-da-dup. What we call that the S1, S2 sounds normally, but then if you start to hear the S3 and S4 sounds of heart valve shutting, it suggests a slowing of the conduction system, usually due to scar tissue. So, you know, for those that are really good at differentiating sound, you would hear somewhat of a difference between the heavy closing of the atrioventricular valves, which is your first heart valve sound, lub, and then the slapping of your semilunar valves, dup, lub, dup, lub, dup, lub, dup, lub, dup. All right. And so those are the sounds that you hear from the heart of the valves closing, of the valves actually shutting. So here's, again, listen to the closing sound of this mitral valve.
Thin tissues, called chordae tendineae, hold your valves in place during the forceful contractions of your ventricles. Blood leaving the ventricle.
Did you hear that? Right? So that's what you hear when listening to a person's heart rate or heartbeat. All right, let me go to the next part. Right there.
In order to pump blood more efficiently, your heart muscle, called myocardium, is arranged in a unique pattern. 3 layers of myocardium wrap around the lower part of your heart. They twist and tighten in different directions to push blood through your heart.
And so because there are those 3 layers of those, really those weaves of muscle fiber, they look like they're forming those intersecting beams like we saw when going back to last semester, looking at spongy bone versus compact bone. We described those beams of spongy bone as the trabecular bone, which trabeculae in Latin means little beams. So what you find are these thin beams of muscle, which is trabeculae carnae, in 3 layers, forming a nice weave, some that are diagonal and some that are circular, so that the overall effect of the contraction is a squeezing, not just a contracting, a narrowing, but a full just twist squeezing. It's twisting and squeezing at the same time, which helps ejectfully force blood out of the chamber.
When special cells, called pacemaker cells, generate electrical signals inside your heart, the heart muscle cells, called myocytes, contract as a group.
So imagine, if you will, that the heart had its own nervous system, its own nerves. And just like a nerve generating an action potential, and we saw the action potential traveling down the axon to the end of the axon, well, the same thing happens to these pacemaker cells. They're built like neurons. They're built with those sodium and potassium channels. And as sodium floods in and potassium rushes out and it creates a negative charge, there's a little bit of an electrical current that travels down these wires. Well, the muscle is so sensitive as far as calcium to the electricity going along those wires that as that electrical action potential travels past the muscle, it releases calcium ions into the muscle fiber. And if you remember from first semester, for those that have the first semester already, when calcium is introduced into a muscle fiber, it binds to proteins, unbinding, moving tropomyosin off of the binding site, and actin and myosin can pull on each other. The muscle contraction of the heart is no different than any other muscle contraction anywhere else. It's still myosin pulling on actin. All the electrical current does of the action potential of the conduction system is cause calcium channels to open right behind the signal. So the way I want you to visualize conduction of the heart is no different than if you have ever gone to a dog racing track or seen it on TV. When the gates open and the dogs start running, around the interior of the track is a little what's called a rabbit. It's an electrical box that goes along the interior of the oval of the track, and the dogs start chasing this rabbit, right? They chase this thing because they know there's a reward if they get it. So they use the rabbit around the track, the dogs chase it, and the winning dog is so if you're sitting there watching, as the rabbit goes by, that's the electrical signal of the heart, and then the pack of dogs comes by, that's the contraction of the heart muscle. So if you notice this, we look back on it, okay, there's the wiring system. You can see it's lit up like an electrical lighting board, and as that impulse right here comes along the wiring of the heart, the muscle's going to contract to the rhythm of that electrical impulse. So what we see is that you've got the heart muscle, and it's surrounded by these pacemaker cells, these neuron type cells. And as the electrical impulse or the action potential of the, very much like a nerve's action potential, goes across the wiring, first comes the impulse, and then it causes contraction of all these heart muscle. So as long as you can maintain a steady rate and rhythm of that electrical impulse, the heart's going to contract. And just to let you know, the heart does not need the brain to tell it to contract or relax. The heart's conduction system works on its own, which means you can take the heart out of the body and it will contract and relax on its own until it runs out of energy. It's got to feed itself. So if you take it out of the body, it's not going to have blood and it's going to die. But the point being is that the nervous system doesn't tell your heart to contract or relax. The heart contracts and relaxes on its own. All your nervous system does is says faster or slower. It is important for your heart to maintain its own self-conduction. And the way it works is that the cells of the conduction system that are closest to the right atrium have the most channels of open sodium-potassium gates, which means that if there's a contraction, you'll always start the leaking of sodium and potassium. You'll start that action potential always at the right atrium, and it follows that pattern of conduction cells, which we'll go over in a bit.
Called myocytes, contract as a group. Your heart is divided into left and right halves, which work together like a dual pump. On the right side of your heart, deoxygenated blood from your body's tissues flows through large veins called the superior and inferior vena cava into your right atrium. Next, the blood moves into your right ventricle, which contracts and sends blood out of your heart to your lungs to gather oxygen and get rid of carbon dioxide. On the left side of your heart, oxygen-rich blood from your lungs flows through your pulmonary veins into your left atrium. The blood then moves into your left ventricle, which contracts and sends blood out of your heart through the aorta to feed your cells and tissues. The first branches off your aorta are the coronary arteries, which supply your heart muscle with oxygen and nutrients.
So in other words, the blood coming out of the aorta that goes right into this vessel called the coronary, this is the right coronary artery, is going to come down and then branch to the heart and feed the heart. Now, the simplest way of saying it is the blood that's going through the heart, through the atria, through the ventricles, is going through way too fast to actually feed the heart. So it actually has small blood vessels around the outside that then branch and branch and branch. And those are what feed the muscle so that it can always contract and relax, always has the oxygen and the energy resources necessary to keep the heart muscle alive. Those are the things that get blocked, usually by cholesterol, right? What we call atherosclerosis. And then surgeons have to bypass. So if you ever heard, oh, I had a triple bypass, a quadruple bypass. Well, what they did was they harvested a vessel from usually the leg. They connect it to the blood vessel here before the obstruction, and then they pass it to the branches after the obstruction so that the heart can get regular blood flow again to itself. So that's when there's a blockage of the artery, what we call an atherosclerotic buildup or blockage. All right.
At the top of your aorta, arteries branch off to carry blood to your head and arms. Arteries branching from the middle and lower parts of your aorta supply blood to the rest of your body. Your heart beats an average of 60 to 100 beats per minute. In that 1 minute, your heart pumps about 5 quarts of blood through your arteries, delivering a steady stream of oxygen and nutrients all over your body.
This is the quickest way to clear out stuck poop.
5.
All right. Let's do one more.
The heart is responsible for delivering blood to all parts of your body. It supplies oxygen and other nutrients where needed. The arteries carry oxygen-rich blood away from your heart to nourish your body. Veins carry oxygen-poor blood from your body to your heart. The pump. Your heart is actually 2 pumps that work side by side to move blood around your body. The right side of your heart pumps blood to your lungs to receive oxygen. The left side sends the oxygen-filled blood out to your body. Each side of your heart has 2 compartments or chambers. The top chambers are called the atria, and the bottom ones are called the ventricles. The 4 valves act like one-way gates and keep blood flowing from one chamber of your heart to the other without moving backward. These are the tricuspid valve, the pulmonic valve, the mitral valve, and the aortic valve. The tricuspid valve and mitral valve are located between the atria and the ventricles. The pulmonic valve and aortic valve are located between the ventricles and the major blood vessels leaving your heart. When the atria become filled with blood, the walls of the chambers squeeze or contract and the blood gushes through the mitral and tricuspid valves into the ventricles. Once the ventricles are filled, the valves close. The muscles in the ventricles then contract, which forces open the pulmonic valve and the aortic valve. Blood coming out of the right ventricle goes to your lungs. Blood coming out of the left ventricle goes into the aorta and then to the arteries where it is distributed to all parts of your body. When the contraction ends and the ventricles begin to relax, the pulmonic and aortic valves snap shut. This action happens quickly and is what causes the familiar lub-dub rhythm called your heartbeat. The electrical system. The rhythm of your heart is controlled by a built-in electrical system. The SA node is where your heartbeat begins. It is sometimes called your heart's natural pacemaker. The SA node is located in the right atrium. It is made up of special pacemaker cells that send impulses to the AV node. The AV node is in the center of your heart and acts as a relay between the atria and the ventricles. When the SA node fires, the atria contract, and an impulse passes to the AV node. Once the impulse passes through the AV node, it travels down through nerve fibers to the bottom of the ventricles, causing the ventricles to contract and squeeze blood out of your heart. Your heart, like any muscle, requires its own supply of blood. The coronary arteries carry oxygen-rich blood to your heart muscle. Veins carry blood depleted of oxygen away from the heart muscle. Things to remember. Your heart is a large pump, powered by its own electrical system. Valves help keep blood flowing from chamber to chamber and from chamber to the body in an organized fashion. Your heart helps to recycle blood by sending oxygen-depleted blood to the lungs to be refreshed, and oxygen-rich blood back out to the body. Thanks for watching.
All right, let's go back to a picture here. Right there. Okay. So he called these nerves, which they're nerve-like, but they're not truly nerves because they're not part of the nervous system. They're part of the heart. Is it an electrical system? Is it a heart's own version of a nervous system? You could argue that, yes. So let's backtrack to a bigger version, a closer view of all of that. Right there. All right. So it all starts right here. Now, this makes it look like it's inside the atrium. It's actually on the outside, not the true outside, but if you were to remove the epicardium, which is the sheath of connective tissue that surrounds the outer heart, and you were to look at the beginning of the myocardium, which is the muscle of the heart, this node, which is kind of like a ganglion of nerve, but it's called a node in the heart, a node because it's a nodule. It's a small lump or node. It's embedded into a depression in the myocardium of the right atrium. It's actually referred to as the sinus of the atrium. There's a muscular depression, and that node is embedded into it. The sinoatrial node, because it's a node in the atrial sinus. The cells of the sinoatrial node that, again, are neuron-like have the absolute, if you will, leakiest gates of that sodium-potassium channeling system that creates the static charge. In fact, they're so leaky, they're always open. All right? The gates are open, which means that after heart contraction has occurred, when the whole, if you will, sodium-potassium pump is engaged to where you're reestablishing the sodium and the potassium levels inside and outside of your cells, well, the cells of the node are so open that all of a sudden the sodium starts leaking again. And as you get further and further away from the right atrium, going down into the outside of the ventricles, the channels of those sodium potassium gates get farther apart and more closed. So let me give you an example of the heart starting. You may have seen on TV or in the movies, or maybe even witnessed in real life, doctors or medical personnel having to use the two electrical paddles where they turn it on, they say clear, and boom, and the person jumps. The device is called a defibrillator. What happens is that heart muscle is supposed to contract in rhythm and should be uniform. If for some reason heart muscle starts to get to where fibers are contracting out of rhythm, or you're seeing more of a rippling of contraction rather than a full contraction, it interrupts the ability of muscle to respond to the electrical signaling. So the defibrillator is a device that doesn't start your heart. The defibrillator is a device that stops your heart. There's so much electricity going through the heart that every heart muscle contracts at the same time. Every action potential is created at the same time all through the heart. And then the conduction system is supposed to start new again at the sinoatrial node. And if the conduction system starts going through with a rhythm again and the heart starts contracting to the rhythm again, the heartbeat is again on a monitor back to a more regular rhythm. So on Baywatch or in the movies, every time they defibrillate, boom, they bring it back to life. The person's heart is working great again. No big deal. In a true hospital setting, when a person codes or basically has a cardiac event, when they pull out the defibrillator, they may establish for a few minutes anyway the normal rate and rhythm of the heart until it goes through that chaos again. So for many, after so many times of defibrillating, they're put on what's called a DNR, a do not resuscitate, and then that person's allowed to, not have to go through the continuous process of being defibrillated. Essentially, it's knowing that you're not going to be able to restore the full use of the heart, and the person is going to succumb to the cardiac event until there's full cardiac arrest. Cardiac arrest is when the heart stops. A heart attack, just to let you know, is not the heart stopping. A heart attack is where heart muscle becomes injured or dies because of blood flow being obstructed, where it creates an arrhythmia. And if those arrhythmias aren't corrected, then eventually the heart will go into arrest. So the heart attack is the event that starts it all, but it's not until cardiac arrest that a person dies from it. The flatlining of the EKG that you see in the movies or on TV, where all of a sudden that's cardiac arrest, which means the heart has stopped beating. So all of the conduction starts here in the sinoatrial node, which is why anatomists refer to the node as the natural pacemaker of the heart. The sinoatrial node is the natural pacemaker of the heart. And as the wiring of the node extends out, it branches around the right atrium and over to the left atrium. There is one branch that continues through the atrial septum to the atrioventricular node. What happens is when that goes off, within fractions of a second, the impulse travels across the right atrium and the left atrium, and the contraction of muscle of the atria occurs following the impulse. Now, if for some reason that impulse went through the entirety of the heart, all of the muscle of the heart would contract virtually at the same time, and then you do not have the effectiveness of the pump. So what you really need to do is have the initial signaling go around just the atria and make sure you can delay the signal until the atria are finished contracting. And that is the job of the node that is positioned between the right atrium and the right ventricle, because it's right embedded between the right atrium and the right ventricle. It's called the atrioventricular node. Its job is to delay the impulse to allow the two atria to finish their contraction. Once the atria have fully contracted, the AV node lets the signal continue down through the ventricular septum. They initially call this the bundle of His, H-I-S, which becomes the right and left bundle branches. Those bundle branches go through the septum and then around the outside of the right ventricle and around the outside of the left ventricle, where they branch outward through the muscle of the ventricles. They're then called Purkinje fibers. And at the end of the branching, the impulse comes to an end, but by then, a new impulse has already started at the right atrium for the next set. So it starts on the right, goes around right to left, gets delayed. The atria finish their contraction. Then as it goes through the septum and around the outside, the two ventricles contract as the atria are filling. So the reason why the right side starts slightly before the left side and ends just before the left side is because the nodes are built into the right side of the heart. So the right side is receiving the signaling of impulse slightly faster than the left side of both the atria and the ventricles. Now, if somebody has a heart attack, and it usually affects the left ventricle because there were many more branches of the left coronary artery to feed the bigger muscle of the left ventricle than the right, there's often obstruction or what we call a myocardial event because of ischemia, not enough blood supply to the heart muscle, and then the heart muscle becomes tissue damage. Once there's tissue damage or infarct, now you have the repair, and that sometimes means scar tissue. And if the scar tissue affects the branching of any of the conduction system, the scar tissue will actually slow the rate at which conduction goes through the heart. And then you'll be able to physically hear the split between the closing of the valves, because the right side will contract and relax a lot faster than the left side contracts and relaxes, creating 4 separate sounds. So there are some anatomy classes where you have to know every bit of the conduction system. You have to know the right atrioventricular node. You have to know the right sinoatrial node, the sinoatrial node on the right. You have to know the atrioventricular node, again, on the right. You have to know the bundle of His and then the bundle branches and the Purkinje fibers. For me, no. But there is one thing that I have seen on licensure tests relative to heart conduction, and that is, what is the natural pacemaker called? So if there's one thing to know about the conduction system, it's the sinoatrial node. Let me show you that in action, okay? Let me show you
causing the
heart conduction system in action. Heart conduction system. And by the way, when you see an EKG, right? Let me show you what I mean by EKG. When you see the EKG, look on this video right here, you see how there's the green line and it says P wave and then QRS wave. That is known as an electrocardiogram. There you go. The Alia Medical did it. And the EKG is nothing more than what the conduction system's doing and where in the heart is the impulse. So we know exactly where the impulse is when we see the P wave and then the QRS wave of ventricular contraction, and then the delay between the S and T, and then it starts over again. So every wave is a heartbeat. Every part of the wave is some point at which the conduction system's in the heart. This is the simplicity of heart conduction.
The heart is a muscular organ with 4 chambers. Blood collects in the heart's 2 upper chambers, or atria, before filling the 2 lower chambers, or ventricles. When the ventricles contract, blood in the right ventricle is pumped to the lungs and blood in the left ventricle is pumped to the rest of the body. The heart has a natural pacemaker called the sinoatrial node, or SA node. The pacemaker controls the heart rate by precisely determining when the muscles of the atria and ventricles contract. The electrical signal produced by the SA node reaches the ventricles through a narrow pathway that includes the so-called AV node and bundle branches. Taken together, these pathways are referred to as the conduction system of the heart.
Thinking I'm gonna start cutting carbs. I need to drop my belly fat.
If you want to drop.
Your heart is a muscle that works continuously, much like a pump. Each beat of your heart is set in motion by an electrical signal from within your heart muscle. The electrical activity is recorded by an electrocardiogram, known as an EKG or ECG. Each beat of your heart begins with an electrical signal from the sinoatrial node, also known as the SA node. The SA node is located in your heart's right atrium. When your heart's right atrium is full with blood, the electrical signal spreads across the cells of your heart's right and left atria. This signal causes the atria to contract, or squeeze. This pumps blood through the open valves from the atria into both ventricles. The P wave on the EKG marks the contraction of your heart's atria. The signal arrives at the atrioventricular or AV node near the ventricles. Here it is slowed for an instant to allow your heart's right and left ventricles to fill with blood. On an EKG, this interval is represented by the start of the line segment between the P and Q wave. The signal is released and moves next to the bundle of His located in your heart's ventricles. From the bundle of His, the signal fibers divide into left and right bundle branches which run through your heart septum. On the EKG, this is represented by the Q wave. The signal leaves the left and right bundle branches through the Purkinje fibers that connect directly to the cells in the walls of your heart's ventricles. The signal spreads quickly across your heart's ventricles. As the signal spreads across the cells of the ventricle walls, both ventricles contract, but not at exactly the same moment. The left ventricle of your heart contracts an instant before the right ventricle. On an EKG, the R wave marks the contraction of your heart's left ventricle. The S wave marks the contraction of your heart's right ventricle. The contraction of your heart's right ventricle pushes blood through the pulmonary valve to your lungs. The contraction of your heart's left ventricle pushes blood through the aortic valve to the rest of your body. As the signal passes, the walls of your heart's ventricles relax and await the next signal. On the EKG, the T wave marks the point at which your heart's ventricles are relaxing. This process continues over and over.
And that is heart conduction.
Your heart's electrical system includes three.
All right. Oh,
The heart is responsible.
okay. So let's make sure that we've covered everything that we need to cover with the heart. All right. So we got the heart, a muscular organ that pumps the blood. It's located behind the sternum, again, like a double clenched fist, set behind the sternum, but tilted so that the apex of the ventricles is off the midline to the left. The right side of the heart is responsible for pumping blood to the lungs. So that means the blood going through the right side is oxygen poor. Once blood has gone through the lungs, it comes back to the left side of the heart, oxygen rich, gets pumped through the left side of the heart, out to the rest of the body to feed the body oxygen rich blood. So again, the arrowing, if we zoom in on the heart, we're coming into this right atrium, either from the lower body or from the upper body or the heart itself, from the coronary vessels. And then that blood goes through the right atrium, through the tricuspid valve into the right ventricle, where when the right ventricle pumps and contracts, it pushes blood through the pulmonic or pulmonary valve into the pulmonary trunk, where either blood will go into the right pulmonary artery, the left pulmonary artery, to the lungs, and in the lungs get oxygenated. The oxygen-rich blood then returns from the left lung through the left pulmonary veins, from the right lung through the right pulmonary veins, both dumping into the left atrium, where blood from the left atrium gets pumped through the open mitral or bicuspid valve into the left ventricle, where the strong muscular walls of the left ventricle powerfully contract and force blood very quickly through the aortic valve and into the aorta, where it'll feed the outside of the heart, it'll feed the arms, it'll feed the head, it'll feed the neck, it'll feed the brain, it'll feed the body, everywhere except the lungs. That is blood flow. Again, it is drawn blue on the right because of oxygen poor content. It is drawn red on the left because of oxygen rich content. All right, that's weird. Why am I frozen? There we go. Okay, I think I went too far. Yep. Whoa. I think my salvo slides got mad at me. All right. Going back to where I was. Hopefully I'll get to the right place. All right. So the heart, if you remember from Dr. Ackland's video, was inside of a sac. And that sac's called the pericardial sac. If you look at the picture of me, if you see how I've got my hand inside of a blanket, the pericardial sac is like a blanket around the heart, okay? it is a sac that allows the heart the ability to move, but keeps it from bouncing off the lungs. The inside of the pericardial membrane secretes a lubricant so that the movement of the heart decrease amount of friction, because it's already generating enough heat as it is. That's probably why there's a nice generous coating of fat on the heart. Some say that the coating of fat on the heart is there in case you need extra energy, that there's the ability to go into that fat and get sugar. I don't know if I buy it. I know that there's a lot of heat generated from muscle contraction, and I believe that the heart's fat does a good job of absorbing some of that heat away from the heart into the fat so that it can dissipate some of the heat. That's why I believe that there's heart fat, but there are differences of opinion. Either way, the pericardial sac, not the fat on the heart itself, but the pericardial sac that holds the heart, is there to encase the heart, protect the heart, and provide a lubrication for the heart. There is a condition that affects the pericardial sac that we call pericarditis, and that's when there's actual infection in the sac, in the fluids of the sac. And even though that's not directly affecting the heart, it has an effect upon the heart because of all the inflammation around the heart. So it's very uncomfortable in the chest. It's usually associated with a moderate to high fever. It can cause heart irregularities as far as rhythm and rate, but it's not as damaging to the heart as heart muscle problems itself. In other words, if you look at the heart, if we actually talk about the heart, there's an outer sausage casing of the heart called epicardium. And that's where we find the coronary vessels around the epicardial surface. But if you remove that sausage layer, now you've got those 3 layers of heart muscle called the myocardium. And that's the actual forceful contraction of the heart. That's the tissue of the heart that we want to make sure is the most functionable, that we want to the least have injuries and problems with. So we want to make sure there's plenty of blood to the myocardium. We want to make sure there's plenty of protection of the myocardium. And then there's a thin inner lining called endocardium. And again, this is the outer sausage casing of the heart. It's the epicardium. We see that 2-ply epicardium out here. Then we've got the actual muscle of the heart. That's the myocardium. You can see a blood vessel there feeding the myocardium, and then a thin inner membrane of endocardium. Look, the only thing I think you should really focus on is myocardium, because it's the myocardium, that part of the heart, that's damaged with heart attacks. Myocardial infarct is damage to the heart muscle layer of the heart. Now, are there people that have viruses to the heart that we call cardiomyopathies, cardiomuscle pathologies, bacterial infections, viral infections, fungal infections? Sure. Most people that have fungal infections or bacterial infections affecting the heart, there's some kind of immune compromise, HIV, some other septic infection in the blood. The majority of people don't typically have a myocardial issue other than, say, viruses that they might have picked up in the hospital. The inner lining of the heart can end up infected because of some infection coming through the heart. And so the endocarditis can be very painful and can decrease the amount of overall contractility. Not as bad as viruses of cardiomyopathies, where the heart just doesn't have the strength. It's so swollen, it doesn't have the strength to beat. Again, those are often hospital acquired. Somebody goes in the hospital for one thing, and then they end up with a virus that affects their heart to where now they're concerned about a cardiac event. But again, way more heart problems exist with obstructing blood flow to the heart because of atherosclerosis or some kind of bleed, like a hemorrhage. And then that causes a myocardial damage, an infarct, and that's much more common than an infection to the heart itself. All right, so there are the 2 atria, which are the inlet chambers of the heart, right side receiving blood from the body, left side receiving blood from the lungs, and the 2 pumping chambers or ventricles, again, right ventricle pumping blood to the lungs to go get oxygen, left ventricle pumping blood to the body, oxygen rich to provide all that benefit to the tissues of your body. The heart valves are relatively avascular, which means that you don't have to have a rich supply of blood to the valves. They are essentially like a piece of connective tissue or cartilage that is, opening and closing to the pressures of the chambers of the heart. The very flimsy valves of the aortic or the pulmonic valves, the pulmonary aortic valves, they're very flimsy, and there usually isn't any issue except for when the aorta starts to change shape with age. Sometimes that affects the closing of the aortic valve. And so some people, as they get older in life, start having a little bit of the regurg into the left ventricle because of the change of shape of the aorta. Again, that's not terribly uncommon, but much more common as far as heart valve issues are problems with the mitral valve, the bicuspid valve on the left side of the heart between the left atrium and left ventricle, because a slight misshape to that valve, the leaflets don't close properly. And so these are kids that grow into adults always having some kind of murmur or some kind of backflow, and they develop full prolapses. And by the time they're middle-aged adults, there's so much backflow into the atrium on the left that they get really short-winded, fatigued, short of breath, because they just don't have that regular outflow of blood coming from the heart because there's too much backflow. So those individuals often get heart valve replacements, like a mitral valve replacement. You can do a mechanical valve, which when we hear the valve, you can actually hear the metal clinking shut. But that person's usually on blood thinners the rest of his or her life as a result. But because the valves are relatively avascular, you can use a donor valve. In fact, it doesn't even have to be from a human. And it's a lot cheaper to harvest valves from a heart of a cow or a pig than it is a human. So many people that have heart valve replacements, based upon their body size, may choose to have the bovine or the porcine valve. The surgeon finds the right size valve and then basically sews it in place. And that valve, which has a life expectancy of another 10 to 15 years, acts to replace the damaged valve that the person had. So it's really quite impressive that you can use a cow's heart valve or a pig's heart valve in replace of yours, but that's the nature of it being not needing blood supply, and it tends to be accepted as self, not attacked as a foreign tissue. Those are the heart valves. The atrioventricular valves are located between the atria and the ventricles. The bicuspid has two leaflets. It's also called the mitral valve because of that bishop's mitre appearance. The tricuspid valve has an extra leaflet, so it's not quite as mitre looking. So it's called the tricuspid valve. The tricuspid valve is between the right atrium and right ventricle, so it's the right atrioventricular valve. The bicuspid or the mitral valve is between the left atrium and left ventricle, so it's the left atrioventricular valve. Those are the ones, again, they look like, if you will, they look like teepees, like tents, extending from the aorta and into the ventricles. They're not these little parachute looking things. They're full, all out tent looking things, and they've got those tendon cords connected to them to prevent prolapse. They're bigger, they're heavier, they're louder, they thud shut. But the semilunar valves, they're flimsy, they're loose, they're transparent, they're curved at their base, and that slight little back pressure causes them to shut. They slap shut. So the aortic one prevents aorta blood going back into the left ventricle. The pulmonary one, called the pulmonic or pulmonary valve, prevents blood from the pulmonary trunk going back into the right ventricle. And they're more of a slapping sound when they shut of the lub up. So again, bicuspid is between the left side atrium and ventricle, and the tricuspid is between the right side atrium and ventricle. Those are atrioventricular. But semilunar half moon valves, again, they're flimsy. They're named for the vessel they go into, the aorta or the pulmonary trunk. Here are the AV valves. Again, there's the TP look. And then the semilunar valves. Lubbed up, lubbed up. Change those to P's instead of LUBB or DUBB. And when we were in school, it's just LUB and DUB, but who cares? Change it to lubbed up, lubbed up, lubbed up, lubbed up, lubbed up. Why is it a lower pitch sound? Because they're heavier, thicker valves. Why is it a higher pitch? Because it's more of a flimsy slap. Lubbed up, lubbed up, lubbed up. And just to let you know, murmur, 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 murmur. That is something you can hear when there's a failure of a full closure of a valve where blood is going against it and there's a bit of a rub. The word murmur is actually the sound you hear, what is known as an onomatopoeia, if I'm not mistaken, where the word is the sound that you hear. Murmur, 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 murmur. As far as the heart, it's got to feed itself. It's got to make sure that the muscle of the heart is constantly getting oxygen-rich, energy-rich blood, and that's through two small coronary arteries that leave the aorta at the base of the aorta and wrap around the left and right side of the heart as crowns of vessels or coronary vessels. And that way, the heart muscle can get from the coronary arteries oxygen-rich blood to the myocardium. And then once that blood is used, the blood uses veins into a sinus return back into the right atrium to start the process all over again. All right, blood flow and move the heart. We did that again, enter the right atrium, right ventricle to the lungs, left atrium, left ventricle to the body. All right, so that's all the staging there. And then the cardiac conduction system is the electrical stuff going through the heart. It always starts at the sinoatrial node. Please, 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 in your notes, and maybe in the notes that I send to you, the sinoatrial node equals the body's natural pacemaker, the heart's natural pacemaker. The pacemaker of the heart is the sinoatrial node. That's where it all starts. That's what maintains the 60 to 90, 60 to 100 beats per minute. That is the key to maintaining a regular, steady rate and rhythm of the heart. Yeah, let's see if it says it'll be in your notes. Copy that. Great, great, perfect. The rest of it, as far as the AV node to the bundle, to the bundle branches, to the Purkinje fibers, not that important. I have not seen any of those as far as that intricate of questioning on a licensure test, but I have seen sinoatrial node stuff. So pacemaker of the heart, sinoatrial node, just know that there's a pathway from the atria through the center of the heart, around the outside, around the outside, around the outside. I feel like Eminem. That way, it always goes from the apex around the outside. So it squeezes from the apex up, pushing the blood toward the pulmonary trunk and toward the aorta. That is the conduction system. All right, let's see. Why? There you go. It's 60 to 100 beats per minute, 60 to 90 beats per minute. That's why it averages around 72 beats per minute because of the sinoatrial node, the pacemaker. All right. And then that's what it looks like in the heart. It all starts right there. And then it goes around the right atrium and left atrium. And then it delays in the AV node. Then it goes through the center of the ventricle, around the left side, around the right side. You know, in the video, she said that the left ventricle will start just before the right ventricle. That definitely the right atrium before the left atrium, but my gut still tells me the right ventricle slightly before the left ventricle also. So she may be mistaken. Doesn't matter. It's never going to come back to haunt you. All right. So to end the heart, again, there are two words that will always be beneficial, not for just talking about the heart when it's pumping blood out or when it's filling, but these words carry over to blood pressure, because when the heart is squeezing blood out, that's when the pressure in the arteries is the greatest. And when the ventricles are filling, that's when the pressure in the arteries is the least, which is why there are two numbers to blood pressure. It's systolic, diastolic, systolic, diastolic, systolic, diastolic. Lots of pressure, not so much pressure. Lots of pressure, not so much pressure. And that is a simple description of, are the ventricles pushing blood out or are they filling for the next contraction? If it's systolic, the ventricles are contracting and ejecting blood. If it's diastolic, the ventricles are relaxing and filling with blood. All right. I will pick up on Tuesday with these other things that we measure as far as what stroke volume and cardiac output are. You as massage therapists are never going to have to try to calculate these numbers. All right. But then what I'm going to do is get into the blood vessels and talk about the differences between arteries and veins, and then follow the map of arteries, follow the map of veins, and ultimately get to the capillary level where we can see the actual exchange of blood and the tissues of the body. So It's actually one of my favorite discussions. I love talking about blood vessels. I absolutely love the discussion. So hopefully you can join me on Tuesday and see my excitement when talking about blood vessels. So that is all for today. I'm going to stop the recording and I will send the link here in a bit. Have a wonderful rest of your evening. Class again Tuesday at 3 p.m. Good night.